Oh, okay. Welcome again, everyone, to the second installment of Ragnar's talk. Uh, Again, Ragnar is from the University of Notre Dame in the US, and he'll be telling us now about some actual calculations and results of ab initio nuclear theory. Okay. Please go ahead.
All right. Well, thanks again, Mwande. Again, happy to give the seminar. So last week, I kind of gave more of an introduction about a couple of questions that you might want to be able to address. So I didn't really talk about anything that I had done. And so this week, I'm going to talk more specifically about how to do these calculations. Won't get into terrible details, but kind of give you a picture of what's been happening in the last couple of years, and then highlight basically two specific applications to double beta decay and the connection between the neutron skin of lead and nuclear matter properties. Okay, so, well, hopefully I'll be able to advance. Yes, okay. So the starting point of just thinking about ab initio calculations is the point that all theories are going to be wrong, and especially in nuclear physics, most theories don't know how wrong they are. So we're going to think about how to assess an error bar on a calculation. When you do phenomenology, you have some model and you solve it exactly. So you basically construct your model so that you can solve it. And if we want to put an error bar on that, your model will have some parameters, and you can maybe do some statistical analysis, fitting, do some chi-squared or Bayesian assessment there. But then you also have a parameterization error, that is the way that you chose to set up the problem. You probably left out some physics, and it's hard or basically impossible to know how important what you left out is because you just cooked up this model. But you set it up so you solve it exactly, so there's no error there. But because it's very hard to assess this, you don't really have much of an error bar. So the ab initio way of going about things is you take not the model Hamiltonian, but the true Hamiltonian, and then you solve it systematically. Of course, in nuclear physics, there is no such thing as the one true Hamiltonian. That doesn't make sense at nuclear scales. So what you need to do is to have some sort of a systematic expansion that will get you close enough so that you can do useful things. And so when you do that, you'll still have some parameters. And so there'll be some parametric error, and there'll be a truncation error. And now you do know what you've left out if you have a systematic expansion. So you can try to estimate it. And to do that, you need a crucial ingredient, which is this notion of naturalness. That is, the coefficients of the things you have not included have natural sized coefficient, or natural size. So basically order one once you've assessed all the scales. And that's crucial for estimating what you've left out. And then we have a systematically improvable solution, because in general now we can't solve this thing exactly. So we have truncation error, and we have to estimate that from various sources of all the truncations we made, and you have to go about figuring out what impact that has. But now we have a kind of a recipe or a path for assessing all the error bars, and so this is a useful way forward. Okay, so why is this hard? So we think about just directly solving the many-body bound state problem. It looks like this. It's the time-independent Schrodinger equation, and it's an eigenvalue problem that you see in your undergraduate, usually modern physics. And you can think about this, if we're going to solve this in a many-body problem, you have some particles, and we're going to distribute them across some levels that define our basis, and say we just fill them up to maybe the Fermi level. This looks kind of familiar from last week. I was talking about a Fermi gas. But in principle, you don't have to put them just in the lowest configurations. You can put them in other configurations, and those can contribute to the wave function as well. So we can just label all these different configurations. And then the wave function should then in principle be some linear combination of all of these different configurations. Fine. And then we can make the Hamiltonian a matrix sandwiched between all of these different configurations, because that's how we're going to expand the wave function. And if you use enough configurations, in principle, you will have an exact representation of the wave function. So then this will become a very big matrix. To make it finite, you need to truncate it, but then you just have a matrix eigenvalue problem. So this is just linear algebra, and you solve it. So no big deal, except we start thinking about the combinatorics of this problem. If we want to distribute, say, A particles across n levels, that means we do n choose A, which looks like this. And when n is much larger than A, this essentially scales like n to the power of A, which means we have now exponential growth in the cost of this calculation with system size, which is not desirable. Exponential growth is a painful thing to put on a computer. So that's why, basically, when I was a graduate student, this was the kind of mindset for how we were going to attack the nuclear chart. So just to orient those who are not familiar, what's being shown here is all of the nuclei. So as a function of neutron number and proton number. So this is the whole thing from the deuteron up to lead-208 is here. And then there's things like uranium and super heavy elements go up there. And so this was a figure from some sort of a grant proposal, but it was kind of laying out how you're going to attack the nuclear chart theoretically. At that time, this was divided into kind of three blocks. There's an ab initio block, configuration interaction, which is essentially the shell model is another word for that, and then density functional theory, also known as mean field theory. So I didn't really discuss these two approaches in any detail. They're both phenomenological. So for DFT or mean field theory, it's cheap because you're just working at the mean field level, so you can go much farther and treat systems that are much heavier, many more particles, but you need to have some effective interaction that accounts for the fact that you're only working at the mean field level. And that's where the phenomenology comes in. Likewise, here for configuration interaction, so there you're doing this expansion and matrix diagonalization that I talked about, but you're only choosing a few levels right around the Fermi surface and basically treating all of the lower states as a frozen core. And so you have exponential scaling, but you keep the number of particles relatively small so that exponent stays manageable. So that lets you go farther, but the fact that you're treating everything as a frozen core, you're only treating a few particles, means you have to, again, adjust your parameters in your theory to account for the fact that you're leaving stuff out, and you don't know exactly how that affects the things that you're calculating. So it's, again, phenomenological, and you can make precise calculations, but you don't necessarily know what your error bar is. Finally, here's ab initio calculations, where you just actually do the full calculation, and it was basically consigned to this small corner of the chart where, because of this real exponential scaling, you just can't go to a lot of particles. So this is kind of nice. You have, everybody's got their little region in space that is their domain, and nobody's stepping on each other's toes too badly. And you can kind of think that there's little regions of overlap where then you can kind of connect. Turns out, in the last, fast forward 10 years later, so this is now, again, that chart, neutrons, protons, and, as you go up heavier and heavier. So this is basically that zone of ab initio that was assigned the domain. And what's being plotted here is converged ab initio calculations using a realistic force as a function of year. And as you can see, as the years go on, basically we've gone and pushed outside of this domain and pushed on and on up here into heavy mass 100. And even now 2 years ago, got a calculation up here at lead-208. So we've basically broken that paradigm of kind of everyone having their own little region, and now ab initio calculations are able to reach large chunks of the nuclear chart, which is, I would say, to some extent unexpected as of 10 years ago. And I think it's really exciting because it allows some applications that would just not have been feasible otherwise. Okay, so why is this the case? One very productive and popular method for doing ab initio calculations is called coupled cluster theory. And this was invented for nuclear physics back in the 1950s. So why is it just in the last 10 years that this has happened? So sure, theorists have been getting smarter, but we've also been aided by Moore's law. And in particular, the fact that coupled cluster and some other many-body methods scale not exponentially with the particle number, but polynomially with the particle number. And so what I'm showing here as a function of year, just data taken from Wikipedia here, is the memory available on a computer. So what you can store in RAM in a typical computer since the 60s, and it's been growing exponentially. And what I'm showing in this blue and red bands are just the amount of the data size, the file size that you need to store just matrix elements of the 2-body and 3-body forces that you need to do these calculations in order to get basically typical sizes you need to get converged many-body results. And they're up here. And so you see Moore's laws going, and basically, sure, you have a method, but you can't converge anything because you can't fit enough matrix elements to actually do the calculation until about, say, 2010, 2012, things are starting to happen. You can do 2-body calculations, but you can't include 3-body forces, which I'll talk about briefly. And it just so happens that in the region between 2010 and 2020, that's when we're getting so that you can fit that many matrix elements on a computer. And the size of this band shows basically what you need to store to converge 16 particles, oxygen 16. And up here is what you need to store to calculate lead 208. So this gets you across the entire chart. And this is only a small little jump here because of that polynomial scaling rather than the exponential scaling. So that basically you have this polynomial scaling and you're just waiting for the exponential scaling of Moore's law to catch up. And so what you can see here is another representation of the plot that I was showing previously, is as a function of year, how far you can reach in A, and it kind of goes slowly, painfully, and all of a sudden you hit where these polynomial methods can get converged, and boom, you have this exponential growth because now you're writing Moore's law all the way up. So it's a really exciting time to be working on this. Okay, and so this is just giving kind of an idea of what you can do with an ab initio framework that is harder to do with phenomenology, is you can have a bunch of different methods that all have their own kind of intimidatingly long acronym. But so these are all different ways of solving the many-body problem. And if they all start with the same input force, then they all get the same answer. So what I'm showing here is a function of mass number. This is the ground state energy of various oxygen isotopes. So oxygen 16 here, all the way out to oxygen 28, which doesn't exist. And in all of these methods can calculate. Some can only calculate in certain instances because of their approximation scheme. But you can see that basically whenever multiple methods are able to calculate something, they generally agree. And so this is, again, that's something that you can do only with an ab initio framework, because if you're doing this in a phenomenological framework, you're basically tuning your potential to make up for the deficiencies in your many-body method. And so you can't share the same interaction across different methods because the interaction has to be tuned to your method. Here, you're just solving the problem and everybody's getting the same answer, which is a really satisfying result there. Things are going well. Okay, so now I just want to briefly talk about how we systematically treat the nuclear force. The inputs there, I'm not going to talk about it at any great length because that would be at least a seminar on its own, but I'm just going to roughly summarize it that in modern ab initio calculations, essentially everybody is using interactions derived within the framework of chiral effective field theory. And if you see a talk where people are discussing chiral effective field theory, you almost always will see some sort of a figure that looks like this. So the basic, let me just in one slide kind of hand-wavingly say what this is that there is an approximate symmetry of quantum chromodynamics called chiral symmetry, which is because the up and down quarks are light. You have almost a good chiral symmetry, but the symmetry is spontaneously broken. And so in the low energy sector, relevant for nuclear physics, there are at least two important consequences of this spontaneously broken chiral symmetry. And one of those consequences is the pion is basically a Goldstone boson of this spontaneously broken symmetry, which means it is nearly massless. It's not a perfect symmetry, so the pion is just light. It's not exactly massless, but it's light. And so the exchange of a light particle gives you a long range force. So this tells you immediately that the long range part of the nuclear force is dominated by pion exchange. This has been known for a very long time, even before people were talking about chiral symmetry and spontaneous symmetry breaking and all that. But this does give you that another way of understanding that. And it tells you that the pion is different from everything else because it's this basically Goldstone boson. The second important consequence is that as this Goldstone boson, pion coupling will always come, the pion coupling to other fields will always come with a derivative, which is, basically a momentum. So that means that at low momenta, the pion is then going to be weakly coupled. So you'll have not a strong coupling, but a weak coupling. And so this is something that you can do in perturbation theory. You can treat systematically. So what that means is that at low momenta, we have essentially a light scale, which I'll indicate here, which corresponds to the pion mass. And then this is the Fermi momentum of nucleons in a nucleus. So there's a typical momentum that nucleons will have inside of a nucleus. And then at higher scales, we'll have other meson masses, so rho meson or the omega, and the nucleon mass, and everything else that comes up in QCD has something of a higher scale. And so what you can do is at low momentum, you expand in a ratio of these light scales to these heavy scales. And so now you have a systematic expansion scheme. And so that shows up like this. So Q is basically just this ratio of the low momentum to the high momentum. So you have Q to the power 0. For reasons of symmetry, there's no Q to the power 1. So the next you have Q to the power 2 and 3 and 4 and 5 and so on. And this very naturally tells you that at some order, there's going to be not just these two body forces, but there'll be 3 body forces and eventually 4 body forces. But it also tells you that those don't come in at leading order, they are subleading, which is why people have been getting away with just treating 2 body forces for a long time. I should probably tell what these little symbols mean. So here the solid lines are nucleons and the dashed lines are pions. So this diagram here represents a simple 1 pion exchange between 2 nucleons. And here this just represents a zero range contact interaction between 2 nucleons, so that you essentially lump all of the short range physics into this interaction. And at higher orders, then you can have this coming along with a derivative and various other terms. And so what happens is that everything that gets lumped in here, you have a constant, a coefficient in front of that. It's called a low energy constant. And that needs to be fit to data. And as you go on, there becomes more and more of these low energy constants that you need to fit to data, but it's a finite number of them. And so you can systematically go on and fit these low energy constants. And an important feature here is that once you pull out all of the physical mass scales, the low energy constants should be dimensionless numbers of order 1, so that even if you don't fit them, you have some idea of, say, if you only work to in 3 so that's next to leading order, you have some idea of the size of what's missing. Okay, so you may just ask the question that, okay, you need to fit these low energy constants. Isn't this an elaborate form of phenomenology? Because you still have all these free parameters, and it's exactly this point that you have naturalness, which is to say these coefficients should be order 1. So you can estimate the size of what you left out. And so here is just a kind of a pretty picture application of using this scheme from a recent-ish paper. They're looking at nuclear matter as a function of density. I've cut off the y-axis, but this is just the energy per particle of nuclear matter. And you can work at leading order. And you can see that your error bars blow up because you're doing a low momentum expansion. And as you go to higher densities, now the Fermi momentum goes up. And so that ratio of scales, momentum over the breakdown scale, becomes a not such a small number. And so your error bar blows up. So then you go to next to leading order and you have something that agrees, and then it also has error bars that blow up, but they're smaller. Next to leading order, and you have smaller error bars still agreeing with the previous orders. And then next to leading order, now you're getting something that has some decent precision. And so now you can actually have a systematic scheme, and you actually can check that what you're doing makes sense, that you're converging, and that your error assumed from a previous order is consistent with what you calculate at the next order. Okay, so I had mentioned briefly that coupled cluster, among other methods, is polynomial scaling. And that this polynomial scaling is really key for getting methods that can calculate beyond the lightest systems, getting beyond that little corner, low energy or light mass corner of the nuclear chart. And so basically the idea for doing this is taking the same picture of distributing particles all over the place and reformulating it in terms so that you have some reference configuration, and then you think about stuff as particles and holes out of your reference state. So this would be like just filling up the simplest up to the Fermi level, and then you excite one particle out, and you maybe excite two particles out, and you have some expectation that as you excite more and more particles out, those are going to be higher and higher energy configurations, so they'll contribute less and less to the wave function. And there are a number of various many-body methods that then make expansions not in, or they basically don't just brute force build up a matrix, but now expand various things in terms of these particle hole excitations or various ways of treating that. And they all then have expansions that do not depend on the number of particles, but they depend on the order that you're truncating here, which then scales polynomially rather than exponentially. So I'm just wanted to point out here that there are many ways of doing this, and in the end, I'm going to focus on the one that I work on, just because that's going to be the results that I'll show. Okay. Yes, is there a question here?
Yeah, on the last slide. So
Yep.
just sort of on the idea of, so when you're talking, you wanted a systematic expansion, so you could always have some good estimates of the uncertainty on your calculation.
Yeah.
But look at this slide. If you're doing, a calculation with this, surely you would have some sort of inbuilt. How would you get the uncertainty on these expansions, for example?
Right.
Not when you're picking.
So that's actually the challenge, is that it is more difficult to do this. You still have a systematic way of doing this, in the sense that you have the expectation. Maybe I'll just focus here on coupled cluster, just to have some concrete. Basically, you say that the wave function is going to look like this. So this is an excitation operator acting on. So here's your reference state, and your excitation operator creates one particle, one hole excitations, two particle, two hole excitations, and so on. And because you exponentiate this, you get this thing, one particle, one hole, but then you also get that operator squared, which creates two one particle, one hole excitations, but they're just not correlated. Yeah. And then you have a two particle, two holes, but you can have that squared, so you can get four particle, four hole, as long as they're not correlated. And the idea is that because you have a dominantly two-body interaction, the dominant correlations between various excitations is going to be of a two-body nature. And so that if you have, say, four particles being excited, it's a large chunk of this is going to be a two particle, two hole excitation over here at the same time as a two particle, two hole excitation over here, but not necessarily correlated. But then you can go on and do a more difficult calculation that will then account for those smaller corrections. And you have this expectation that as you go, including T1, T2, T3, the effort goes up, but the correction, the size of the correction goes down. And this is what is seen in coupled cluster, for example. I think there's still, I'll say this in the outlook, that there's still work to be done to put this on firmer footing in terms of rather than just having an expectation and validating it, actually have a quantitative prediction before you do that next order.
Yeah.
But right now it's still a systematic scheme.
Okay. All right.
That's an excellent point, though. Yeah. Okay, so I'll just try to give you an idea of how we're doing this with the this method IMSRG, which is short for the in medium similarity renormalization group, which is why we call it IMSRG, because that's a very long name. So here is the kind of the way you can think about doing this way of solving the many-byte problem, is that we're going to perform a unitary transformation. So we have our initial on the Hamiltonian. So we have our original Hamiltonian, and we get a transformed Hamiltonian by performing a unitary transformation indicated by U here. And so if we think about our Hamiltonian as a giant matrix, and I'm just kind of artificially splitting this up into subblocks, which I've labeled P and Q as kind of for historical reasons, the notation here. And this is not to scale. We're going to say that the P block is small and maybe tractable. So you could solve a problem here, and the Q block is enormous and you can't solve that problem. And just to, for people who don't work on this, I think it's good to have some sort of an idea of how big these things can be. So if we're going to do a diagonalization, we can typically handle something here where this would be on the order of 10 billion states by 10 billion states. You can get some eigenvalues out of that with the Langshos algorithm or various refinements of that. So if you only have 10 billion states in your P subspace, you can handle that. But for these larger systems, the ab initio, these things, this dimension will get something like 10 to the 20 very easily because of this combinatorial growth. And that you just cannot handle. So what we want to do is with this unitary transformation, we want to block diagonalize this giant matrix. So there's this Hamiltonian acting in the P space, there's a Hamiltonian acting in the Q space, and then there's couplings between the two. If we drive those to zero, then we can just diagonalize in this tractable subspace and get, because this is a unitary transformation, we get some eigenvalues of the full Hamiltonian. And usually if you arrange this properly, these will be the lowest ones, which are the interesting states to actually access. And actually the way we achieve this in the IMSRG is, because you need to figure out some way to actually construct this unitary transformation, is we construct it through a flow equation. So what we say is we introduce a numbers of flow parameter that just kind of characterizes, you can think about it like a time, but it characterizes how you're going along in this RG flow. And so you say that unitary transformation, as it obeys a differential equation dictated by the action of something called a generator on the unitary transformation. So that initially unitary transformation is 1 because you're starting at your initial Hamiltonian, and this tells you how it changes as long as you've selected a generator. And it takes 2 or 3 lines of algebra to show that if you've done this, then that means you have a differential equation for your Hamiltonian, which is just a commutator of the generator with your Hamiltonian. So this is your RG flow equation for your Hamiltonian. So at the end, and initially you have your Hamiltonian that you started with, and then this will give you a unitarily transformed Hamiltonian. You can think about this as now you're flowing along in the space of all possible Hamiltonians, and this maps out a trajectory so that in the end you have some other Hamiltonian which is unitarily transformed. And so the generator eta kind of picks out the trajectory that you follow. And if you think about, so this is just 3 dimensions, but of course the parameter space for your all possible Hamiltonians is much larger. But you can imagine if there's one, say, coupling constant in your Hamiltonian that causes problems, you flow along and then go to the place where that's 0. You're living in this plane where that one parameter is 0, but you're still unitarily equivalent. So you can try to go to places where troublesome terms go to 0. And to set this up so that it actually scales polynomially, you write your Hamiltonian out in a second quantized notation. You have maybe some reference energy term, and then you have a one body term and you have a two-body term and so on. So what this is basically saying that there's some component of the Hamiltonian that just changes one particle at a time. That's a one-body operator. Say the kinetic energy would be something that contributes there. And you have two-body operator, so maybe some two-body potential happens there. And these little curly braces just mean that we've used Wick's theorem to write these creation and annihilation operators in normal order with respect to this reference state. So now these are creating particles and holes out of the reference. And so maybe this configuration would be react with create state I, annihilate state J, and so we now have a particle hole configuration there. So now that we've written our Hamiltonian like this RG flow equation means that we'll now have flow equations for each of these parameters. So this reference energy and each of these kind of coupling constants that characterize the one and two body terms. Importantly, the scaling of this effort is not determined by the number of particles, but by which operators we keep. So here we're keeping one-body operators and two-body operators, and that doesn't matter if we're talking about oxygen 16 or lead 208. We're still looking at one-body, two-body operators, and so that turns our scaling from exponential in A to just polynomial in the system size, which in the number of single particle states that we need to include, and so that gives us basically polynomial scaling. Okay, so how do you actually choose this generator? So one choice that's very convenient, if, for example, we wanted to suppress all of the configurations that lead to particle hole excitations out of our simple reference so that we could just treat the simple reference. It's basically the extreme limit of this P space being just one configuration. We just want one configuration decoupled from everything else. We would choose our generator to be those terms in the there are other terms, but predominantly it will be those terms in the potential that take two states and what I'll call whole states down here and scatters them to particle states. So this leads to these two particles interacting and getting scattered up there. If that were zero, then we wouldn't have to worry about that process, and we're decoupling the reference state from the two particle, two whole states. So we choose something that looks like this, and diagrammatically it can look like this, where whole states are kind of look like they're going backwards in time. And then this RG flow equation, kind of schematically, we'll have a flow equation for our coupling constant gamma. And so at a time S plus ds, or flow parameter S plus ds, we'll have our original coupling constant, and then we'll have some other object that comes from this commutator, which when you do commutators, you end up just connecting diagrams together in all the ways that works. So we'll get something that looks like this. We'll have some correction there from connecting this object with this object and maybe some other terms. And then at the next step in the flow, so now 2ds, we have our original, we have this thing, and now we can connect this thing, the generator, or this thing becomes part of our new generator and connect it with that, so we can build up something that looks like this. And there are many other topologies that I'm not showing, but you can kind of get the idea of how everything gets churned back through in this RG flow equation. And so that as you integrate, this builds up all the diagrams in all orders of perturbation theory. So this is not just doing perturbation theory, this is non-perturbative, and you're building all of this stuff up. Okay, so that's essentially all I want to say about the many-body method for now. And I want to just look at some applications in the last half of the talk. So the first application is to the neutron matter equation of state. I talked about this last week. We have neutron stars, and we want to have some idea about how this very dense neutron-rich matter behaves as a function of pressure, energy as a function of pressure or density, if you like. And we have some idea here how symmetric nuclear matter is, where you have protons and roughly equal number of protons and neutrons, because we know that it saturates. And this is where nuclei live, so we have an idea that it should go through here. We don't necessarily know what happens at very high densities, but we have some idea here. pure neutron matter, because we know that we don't have bound systems of just neutrons, so we're not gonna have negative energy, we're gonna have positive energy. But we don't have data of just a bucket of neutrons in the lab, so we don't have this as precisely. We know it's going to probably just go up because there's going to be some repulsion between the neutrons. And the way that you often characterize this, because we have some idea of what symmetric nuclear matter is, the idea of the symmetry energy. So that's the difference in the energy between symmetric nuclear matter and pure neutron matter as a function of the density. So that's the symmetry energy is S of rho of the density. And that's the thing we'd like to know. And I showed this plot last time. So that's this symmetry energy as a function of the density. And these are theoretical calculations. And they're pretty well constrained here around nuclear densities. And then once you go to higher densities, everything blows up. No one knows what's going on. So one way that this is often considered is to take a Taylor expansion around nuclear density. And so that we say that this symmetry energy is basically a constant. This is the symmetry energy at saturation, and then a slope. So basically the linear term and then higher corrections. But basically, you can see here, everybody basically agrees on the first term. They're all at the same point around saturation, but the slope of these at saturation varies wildly. And so we would like to be able to constrain what that slope is. And that really differentiates between all these different theories. Okay, so because we don't have a bucket of neutrons, we want to now relate this to something that we do have in the lab. It turns out that to some extent, the closest thing we have to nuclear matter in the lab is lead-208, a heavy nucleus. And it has been observed, I think, originally around the year 2000, that there's this very strong correlation between this slope parameter that we're interested in, L, and it's called the neutron skin of lead-208. So a neutron skin is just the difference in the proton radius and the neutron radius. Lead-208 has 82 protons and 126 neutrons. And so those extra neutrons need to go somewhere and they maybe stick out a little bit. And basically, you can actually understand this physically, that those two quantities should be related, because out here in the skin, it's pure neutron matter. In here in the interior, there's protons and neutrons, so it's kind of like nuclear, it's symmetric nuclear matter. And the energy difference will tell you, whether the neutrons want to be out here or in here. And especially the density dependence of that will tell you how far out they're willing to go. And if they want to be at a high density or low density area, basically the slope of this symmetry energy will tell how far the neutrons are willing to go out here. And so if you calculate the slope parameter L and the neutron skin in various mean field theories, both relativistic and non-relativistic, they lie on this line. It's almost perfectly on a line. And so the idea is that if you can measure the neutron skin of lead-208, and okay, you just take a point, go over to the line, and then that tells you what the slope parameter is. It's not trivial to measure neutron radii, but it's possible. And so there's this idea of using parity violating electron scattering. This is the PRES experiment at Jefferson Lab. So the idea is that you take an electron and you scatter it off. And if you basically measure the spin coming in and coming out, the polarization of the spin, and look at the two different polarizations, and you take a difference such that you select out the parity violating component, the electromagnetic interaction conserves parity, so you should basically subtract off the electromagnetic interaction, and you'll be left with just the weak interaction, exchanging a Z boson. Electron exchanges a Z boson with lead. And if you look at then the weak charge of the proton and the neutron, the proton weak charge is basically 0. The neutron weak charge is basically -1. And so you're essentially probing the neutron distribution of lead-208. If you just do regular electron scattering, you couple to the electromagnetic charge, which is 1 for the proton, 0 for the neutron, and so you can simultaneously get out the charge distribution, which gives you the protons, and the weak charge distribution, which gets you the neutrons. And you can take the difference and get the skin. It's a difficult experiment, but it was run. Was there a question there?
I think.
No. Okay. So basically, the idea is to do this experiment, measure it, and then extract it out. But I just want to point out a couple of caveats here. Is that first, and this may not end up being a problem, but there's this correlation, but it only shows up in these mean field models, which have been fit to the same data, basically nuclear binding energies and radii. So you may start to worry if there's, because they're all mean field and they're all fit to the same thing, is there a common systematic error? So maybe there's this correlation which is just showing a systematic in the framework. Maybe not. And may also wonder, is there some additional data that you don't usually include in the mean field theory that would also help to constrain L? Because there's this very large range of values which are all predicted by mean field models, and they all do a good job predicting nuclei. So this is really poorly constrained. And so doing an ab initio calculation can help clarify both of these questions. I don't want to go too much into this, but the reason that this only happened in the last couple of years is because going to lead-208 was problematic because of the issue of storing all the 3-body matrix elements you need to do that. And we basically overcame this in 2022 by coming up with a clever storage scheme of only storing exactly the combinations that enter the calculation and reducing the storage by a couple of orders of magnitude, which allows you to do this. And I don't want to talk about what this truncation is, but basically this is, as you go to the right, you're keeping more of the 3-body force, but the cost of storage goes up. And the previous limit was this vertical line. And basically you would want, as you increase this truncation, you want to see convergence, meaning that you've stored enough that your answer is not changing anymore. And the previous limit here, we're just computing lead, or sorry, it's tin 132, so not even lead. But as you look at the energy, if you could only go up to here, there's 18, you would have no sign of convergence at all, so you have no control over the calculation. But now we're able to push it further, so then it flattens out, and we have convergence, so we have control over the calculation. So that was essentially the bottleneck that we needed to overcome only in the last few years to get to lead-208. So we can do it, but there's another problem. As we're doing this, how do we determine these low energy constants, and how do we assess the associated uncertainties there? Because there's actually a question or a consideration that if we just fit the parameters in a kind of traditional way of doing some sort of least squares, we're actually overfitting, because we know that there are further terms that we're throwing out, and those will change our answer. So we have basically a theory error that we need to incorporate in some way. And essentially, you can think about this, that if we are working just at leading order, and this is just some schematic thing that red is a cartoon of a data point, and we make sure that our leading order goes right through the data, we're actually maybe not doing what we should be doing, because at the higher order corrections will move our prediction up there. And we need to account for that somehow. So we need to basically incorporate these theoretical errors in the fitting procedure. And in the end, because we're leaving out something, our predictions should not be numbers, but should be distributions that in some way marginalize over everything that we're leaving out. And this is much better done in a Bayesian statistics framework.
Let me just throw a question in here.
Yes.
I'm used to, in a situation like this, that you just refit when you go to higher orders. You're talking about something different here, I take it.
Yes. So basically, this gives you a way of exploring this distribution, because if you just refit, again, you're going to be overfitting in some sense. So then you become, I guess I should have also put here, basically, when you're fitting or overfitting, you become also kind of connected to the specific data that you use to fit to. And in some sense, if there are maybe 2 or 3 observables and you fit very precisely to one observable, you may not be optimal for the other observable that you want to predict. And so this is basically the goal here will be to not overfit to any one particular observable so that we can now have a better idea of how we're doing for other quantities. For example, the neutron skin, because we're not going to fit to the neutron skin, we're going to predict it. So here's the framework. It's called iterative history matching. It collaborate with statisticians to kind of develop this. We want to minimize the bias introduced by selecting your calibration data. So what we do is we're going to use our calibration data to rule out implausible regions of parameter space. So what that means is that if some observable that we calculate with some point in parameter space is different from the experimental value by more than 3 sigma for any observable, then we call this point C implausible. And so here the sigma needs to include theory and experimental error. And so if it's greater than 3 sigma, then we call that just an implausible point. Don't even worry about that. That's not something that we need to consider. So cartoonishly, if you had 2 parameters, C1, C2, there may be some small region where you get non-implausible values and everything else is implausible. And you can maybe may not be surprised to learn that this was developed by a British person to use this phrase non-implausible rather than just plausible, but it's called non-implausible. So then the idea is that you can then sample from this non-implausible subspace and you get some idea of the range of what is reasonable. And those distributions will be somewhat more conservative. And so here's a kind of a realistic implementation of this, showing all of the, not all of them, but some of the different low energy constants that enter into the Kyrie-Leaf T in 2LO. And you can see that there's actually fairly narrow ranges dictated just by the data we're looking predominantly NP scattering and then few body systems. And one thing that you'll notice is that in particular, these 2 quantities which characterize 3 body forces are the relatively poorly constrained ones, because of course it doesn't even enter when you're looking at proton-neutron scattering. There also, you can identify correlations between various coefficients and so on. So then that's a much smaller region of space because there's lots of low energy constants, 17 in this case. And so you drastically reduce the space, and now you can be sampling from there and have much more reasonable parameter points. And so then this is now summarizing how we did everything in kind of in a Bayesian picture. So what's being shown here, each of these lines is a different observable, and we're showing basically the discrepancy theory minus experiment divided by the total error. So you think about this in units of sigmas. And so the top kind of few here are used to define this non-implausible volume of space. And then we have a couple other observables here, which we then use to define a likelihood, which is something that then enters into Bayes' theorem. So these are the ones we think are going to be informative of quantities that we want to predict. And then pink is going to be the posterior predictive distribution. So this is just a pure prediction. Weighted, or basically the sampled interactions are weighted by the likelihood. So basically, interaction points that do a good job of reproducing the radius and energy and 2+ excitation energy of calcium-48 get a high likelihood, and then that basically dictates their weight in these final distributions. So we can predict dipole polarizabilities, the radius of lead-208, and the energy per particle of lead-208, and things are looking pretty good. The error bars are bigger than you'd get from mean field theory, where things are kind of fit to that, but the experimental data is consistent with our assessed error bars. Now we have a prediction here for the skin of lead-208. That's this pink distribution. And then these are various extractions from experimental probes. And in particular, this is the result of the PREX experiment. And so we can, an interesting question is that correlation that is present in mean field theory still present in ab initio calculations? And so these open symbols show the mean field theory. There's that correlation, and we overlay some sampled calculations from the ab initio, and it lies right on top, which is great. It shows that we see the same correlation, and not just, we also see a correlation, but it lies on the same line, which is very encouraging. We also notice that we kind of run out of steam. We can't go all the way up here where mean field theory goes, in particular onto this point where the PREX experiment came in. And you can actually understand that because there's not just a correlation with nuclear matter, but there's a correlation with the scattering data. Basically, the neutron skin of lead-208 in our ab initio calculations also correlates with neutron-proton scattering in a particular channel, the 1s naught. So this is the one that would correspond to neutrons as well, because you have to have a spin up and spin down neutron. And in the S wave, that's when they can get close to one another. 50 MeV is roughly corresponding to the Fermi momentum in nuclear matter and a nucleus. So it's not maybe surprising that this dictates that same physics. But what we find is that, so what's being plotted here, this little narrow band here is the experimental value for that scattering phase shift. And the purple band is the PREX result for the skin. And so we can move along this band to get closer to the PREX, but we have to go away from the scattering data. And so that basically the explanation here is that the reason we can't go up this way is because we are also constrained by scattering data. Mean field theory does not treat scattering data. That is not in there. So basically it's not incorporated. So it can just push on up because the only thing that gets spoiled is scattering data, which they're not looking at. So this leads to a bit of a tension, which is actually very nicely summarized right here. You can also measure the neutron skin of calcium-48. You can calculate that. And so those lie on a pretty nice line because, as you might expect, neutron skin in one nucleus and another is pretty well correlated. So that's these points. And then the experimental data is over here. So there's looks like a pretty bad tension, right? Of course, you can imagine that this is a 1 sigma statistical error bar. And so if we were right here, that would not be so crazy, in which case the tension would be considerably less. But I think it's really interesting to follow up and do a more precise measurement here, because right now there's very little that we can do to move all the way over to where the central value is. Okay, and in the last 5 minutes, I think I can actually do this, but I want to talk about a second application, and that's for neutrinoless double beta decay, which I talked about last week. And especially mentioning these 2 papers that are still just on the archive. And so I'm motivated, this is interesting, and that we want to do this ab initio. So how do we actually do it? Well, I'll remind you that there's basically this experimental limit from not seeing double beta decay. And this band here is dictated essentially by this nuclear matrix element M0 nu there. And that's the thing that we want to calculate ab initio. This is kind of shows you the situation as of a couple of years ago, that if you use phenomenological models, so these are all the different candidates for double beta decay. This is the nuclear matrix elements, and they get very different answers, sometimes a factor of 2 or 3 different. And basically there's more correlation across method rather than across nucleus. So basically we don't have a very good handle over what this matrix element should be because we don't really know what the method uncertainty is. Right now, the error bar here is just taken from a spread of this, which is not really a proper error bar. So we want to go back and do this more carefully. We did. We can calculate this ab initio. We can do the same trick of now, sampling from a non-implausible distribution, so we can get some idea of the error due to the parameterization, because we're working in a finite order in effective field theory. And here, I didn't mention this for the lead 208 calculation, but in both cases, to assess the many-body error, we use multiple different many-body methods with the same input interaction. You should be getting the same answer out. So the discrepancy between them, it gives you a measure of the many-body. And so that's what's being shown right here. So here is, this is the valence space IMSRG, and this is the in-medium generator coordinate method. So these are two different many-body methods that actually have fairly different expansion schemes, or basically are trying to put in physics in a different way. Eventually they should agree, and we get the same input interaction this point and this point. So that gives us at least some idea of how precisely we're solving the problem. So we can combine all of the different sources of uncertainty, and we can get a distribution from, because we're sampling from this non-implausible volume, and we can generate an error budget. So here is now the double beta decay matrix element with an uncertainty, and we can see how the various sources contribute. So this is the error due to the low energy constants, because we're sampling through this non-implausible space. This is an uncertainty due to the fact that we're truncating at finite order, so we're trying to get some idea of what higher orders will give. This is the error due to basically the many-body solver error. Here's error due to we're using a finite order of the operator corresponding to the neutrinos double beta decay. So that has its own expansion in chiral EFT, including an unknown leading order contact LEC, which was estimated. And so this gives us an error there. And the fact that we're using an emulator for doing our sampling contributes some error, but that's very subleading. So really the dominant sources here are now the many-body error and our sampling of the low energy constants. So that gives us an idea of where to work to try to improve. And just to put this back on that picture for germanium 76, now we have this error bar where this thing gives that full assessed error bar. And if we could eliminate the low energy constant and many-body theory errors, then we'd have this nice tight error, which would be a dramatic improvement over what's being used. So that tells us that we need to go back and hammer away at that, and we can work towards getting a very useful uncertainty for this. And of course, we want to repeat the exercise for the other systems that are being pursued. Okay, so since I'm at my hour time, I will just leave the summary there briefly. And actually, before doing that, I want to thank you for your attention, and thank all of my collaborators. Both of those projects were required lots of different people with lots of expertise. So all of these people worked on these projects, and it wouldn't have happened without these big teams. Okay, so thank you, and I'll just leave this up.
Right. Okay, thank you once again, Ragnar, for that lovely presentation. So, do we have any more questions? Okay, Daniel, please.
I guess it's two sort of random questions. So the first one is, when you're dealing with the renormalization group equation, low parameter S, I've seen cases where that parameter is something completely unphysical and unmeasurable, and some cases where, it's like the energy or something. So
Right.
Is that a meaningful parameter, or is that simply
So-
a constant?
It depends on exactly how you're using this. So, and I basically the same flow parameter applies whether you're doing, it's called in medium SRG or just regular SRG, where you're doing it in vacuum. And when it's used in vacuum, you don't, you basically want to use it, you want it to soften the interaction. Basically, there's this short range repulsion that couples low and high momentum scales and makes it hard to do calculations. So if you get rid of that, it softens the potential. And in that case, you interpret S as, well, you can take a fourth root of it basically and interpret it as a momentum scale. But just working out the units of what this is, so you can rewrite it in terms of a scale which characterizes essentially you can think about in momentum space your potential as a matrix, and then you push it towards a band diagonal and it characterizes the width of that band. So that would be the SRG scale that you push in there. If we're doing this in medium, and often you want to do this block diagonalization, what you do is you actually take S all the way to infinity. So you want this coupling to go exactly to zero. So in some sense, it's still physical. You could probably try to assess some physical quantity with it, but in the end, you want it to go to infinity, and so you don't worry too much about assigning a physical meaning to it.
Okay.
Good question.
I guess another sort of slightly random question is why 3 sigma for the non-plausible area? Was it just a number that was nice, or is there?
So that's why we brought on board statisticians or statistician for these kind of things. But if it basically once things become, you can imagine that if you looked at say 40, okay, if you look at 3 observables, maybe one of them is going to be off by 1 sigma, right? If it's Gaussian. And so 3 sigma is enough that now it's like, for the most part, I can't remember. So it's like, you're in the 99% kind of percentile type thing. And so if it's beyond 3 sigma, you're probably not doing, it probably is an unlikely point. This is probably not just a fluctuation. Now, if you're including 1,000 uncorrelated data in here, then you're maybe going to see some of those, and so you have to worry about that. But I mean, you could say it should be 7 sigma, but then you're going to have a smaller or a larger non-implausible space, and you'll have more points that are really not all that plausible in there. So it's kind of a trade-off between refining the volume and throwing out good points, I guess.
Okay.
Another question?
Of course, yeah.
Oh,
Sure, there are questions. Why couldn't there? If you do your chiral expansion, right, momentum scale ratios versus your RG, I mean, those two things are probably linked in terms of how things converge, right? Can you say anything about this that is understandable to somebody who's not read a paper?
Sure. So these are actually kind of distinct scales. So the momentum scale associated with the breakdown of in chiral T, so that's the thing that goes in the denominator, is a physical scale. It's corresponding to the breakdown scale because there's physics that shows up there. You also have a cutoff because of the field theory, and so you should be independent of that cutoff because that's an artificial thing that you put in there. And the RG scale is also artificial. And so that then you should be independent of that scale. So this is actually, this is nice because if you didn't do the RG step, if you wanted to establish cutoff independence, because so you basically need to move your cutoff higher and higher. And what that does is it makes the potential harder and harder because you have higher and higher momentum components now in your potential. And so it becomes harder to converge. Because you have all this coupling. So you can move your cutoff in the chiral theory higher, and then you can RG evolve it down. Because now you're not using the same operator basis. You're not using the chiral operator basis when you're doing the RG evolution. You're doing this in some sort of momentum space, plane waves, or harmonic oscillator basis. So it's something very generic. And so as you evolve down, you won't necessarily map exactly onto the operator structure of the chiral potential. you'll induce some other structures. But you're doing your power counting up at the original scale where things are good, and then you evolve down, and because it's a unitary evolution, everything is okay. So it's actually a very useful thing to be able to explore cutoff independence. You should then be able to also explore that your RG scale you're independent of your RG scale, because you can fix your cutoff and then calculate a different RG scales, and that should be independent too. Of course, if you do it too hard of an RG scale, it makes the many-body calculation challenging. So there's work to be done still there in being able to nail that down. But over at least a reasonable range, you can establish RG independence.
And there's a lot of stuff, right? I do remember the early days, Ohio State people, right? Frenstall and Perry doing things in vacuum with methods like this. And what always struck me is that they didn't really talk about their generators very much. It seems in what you're doing, you have tightened this down quite a bit more and described this in a more systematic way. Do you have reference for this? Because I would actually like to have a somewhat closer look at these things on the systematics of how you do that.
Yeah, so I mean, in the free space formulation, the one that the furnished we're working on, there's actually been I don't want to say basically no progress in that, but it's been very difficult to beat essentially the first dumb generator they came up with, which is make the generator be the commutator of the potential and the kinetic energy. And there were several years of people trying out different things, exploring new generators, and for free space softening, nothing beats that. So that but no good explanation of why the heck that is good. So why it's good? I mean, it makes sense because the kinetic energy is k squared, momentum squared, and you can actually kind of analyze this. And here, I think I would actually point you to one of the reviews that Dick Fernstall wrote, probably around 2010 or 2011 or something like this. And you can kind of see how it exponentially suppresses terms in terms of the difference in momenta of the bra and the cat. Like if you take a matrix element, you'll get exponential suppression in the difference in those momenta. So it is essentially suppressing as a Gaussian.
It's narrowing the band. Yeah.
Yes, it just narrows the band. And you can see that, but then there are additional terms, which of course have to account for the fact you're throwing out some physics that has to come back in somewhere. But you can basically see that because the kinetic energy goes like k squared, then it suppresses things exponentially like the difference in momentum squared.
Very good. Questions? Okay. So I have one more question, Ragnar. So what was the conclusion on that L there? Can you go to that page where the L appears as a I guess a gradient of some sort? And I just want to know did you succeed in constraining this further? I didn't quite catch that.
Well, so I mean,
yeah.
Yeah, so right now, I think it depends on exactly who you talk to. So I will say I stand by our conclusions here. So basically that you have this range of, and I should mention that outside of this P-Rex experiment, all the other experiments, let me go back here, are more consistent with this. So these are now going to be more model dependent. So that's the downside, but they all kind of end up in there. So in that sense, P-Rex is an outlier. So the result was a little surprising. Again, if you look at this error bar, that is a 1 sigma statistical error bar. So you're going to be inside that 2/3 of the time. So it wouldn't be that crazy to have the point right here, right? I do recognize that it's a very dangerous and probably crazy thing for a theorist to say, well, the experiment's wrong. But it can be wrong. This would just be a statistical fluctuation, and this, so that is basically the easiest explanation to reconcile everything we know. If you go back, and so there are plans to do the same experiment at mines once they build that the facility to do this, and hopefully shrink these error bars down. And if it has the same centroid and just smaller error bars, this actually becomes very difficult to understand, because we didn't just fit our best toy model and say, well, okay, it disagrees. We explored everything that was not implausible, and we're incorporating, like, to get up here, you have to really break the scattering phase shifts, and so this would essentially, I can probably say that this would be a crisis in how we're thinking about nuclear physics, in the sense that we believe that we should be able to understand lead based on nucleon potentials, and if we've done a proper job assessing all of the uncertainties. Now, there could be some sort of a loophole here, in that when we did this, we only worked at one particular cutoff. It was somewhat low, and so maybe the cutoff was too low. We have regulator artifacts, and if you raise the cutoff, then all of a sudden it shifts things up in that direction. I don't actually think it's going to be that's terribly likely, but it's this thing that on the theory side we need to explore. But if this tension remains, then I would call this a crisis for nuclear theory.
Playing with the cutoff would affect probably also the cost of your calculations.
Absolutely. So right now the cutoff was low enough that we didn't have to do SRG evolution to soften it. And SRG evolution is actually pretty expensive, especially because you need so many 3-body matrix elements here. But what you can do is you can go to a higher cutoff and then do, the SRG evolution is doable. You can do it not 1,000,000 times, but you could do it 30 times. And that would be a reasonable, so here we only have some just maybe a couple, 34 points here, 34 samples gives you kind of the distribution. So we could do it. It's just a little bit more painful. But I think that's the next step for us to really show that there's not a major artifact leading to this shift.
Okay, very interesting.
But the mean field calculation seems to go right through the center of that.
Well, I will say that the P-Rex experiment did not measure L. It just measured the skin. So I've lined it up there. I put that there. It can float up and down all you like. So basically, mean field can give you any answer you want.
All right. Any more? Okay, good. All right. Thank you. Let's thank Ragnar again.
Thanks a lot.
Right.
Thanks, that was again a lot of fun.
Yeah, that was fun to pull those together. I like the throwing all the motivation slides in the first